Okay, so here's a problem again. We're going to draw the shear force and bending moment diagram for this structure. We'll start by seeing if we can find out the shear force and bending moment at each end. So we'll have kind of bounds for our equation. So I won't redraw the diagram, but I will assume at these reactions that I have a positive shear. I'll call this point A. And I have a positive shear at B, and I'll call this point B. So we just need to find those values. So I'm going to use right-hand rule when I do my statics for moments. So I'm going to sum moments at A. You could sum moments at B if you like, whichever way you feel more comfortable with. About A, all the applied forces are going to create what kind of moment? Negative. And while I'm thinking about that, I'll go ahead and figure out my concentrated equivalent of this distributed load. It's a rectangle, so the base is 4 meters, the height is 4 kilonewtons per meter, so that's a 16 kilonewton force. And it's going to occur right in the middle, which would be 2 meters from that edge. So now when I'm looking at those forces and how they create moment about A, they're all negative. So the first one would be 8 kilonewtons times a moment arm of just 1, minus 16 kilonewtons, which is the concentrated equivalent force for the distributed load, and acting through that centroid would be 2 plus 2 more, or 4 meters. And then the 4 kilonewton force, and that has a moment arm of 2 plus 4 is 6 plus 1 is 7. I just thought so. Is this a homework problem? Is this your homework problem?
It was similar. It was the last one.
It's 4:30 in the book, yes.
Is that exactly the same problem?
I think so.
Oh, that's a screw up. I didn't mean to do that. Sorry.
It's similar.
Is it similar? I thought
It is similar, different. Wasn't the one in...
I don't know. The one in the book is symmetrical?
All the loads were.
No, it's not the same. No.
It's different enough?
Yeah.
Okay. Sorry, it just suddenly dawned on me. I thought that looked awful familiar. Okay. Well, okay. Sorry about that.
Just that the loads of reaction.
Okay. Well, let's plow on then. So we got the shear at B. Sorry for that disruption. And then that would be, let's see, 2 plus 4 plus 2, that's 8. So we should be able to solve for the shear at B, and I think it's going to be negative, but I'm going to have to compute it, or let you guys compute it. What'd you get?
I got 12.5.
12.5. Somebody else get 12.5?
Yes.
Good. So 12.5 kilonewtons. All right, so to get the reaction at A, I will sum all the forces in the y direction and make sure they're in equilibrium. So looking at my free body diagram, I have the shear at A minus the shear at B, and then all those forces are down. So I have minus 8 kilonewtons, minus 16 kilonewtons, minus 4 kilonewtons. So it looks like the shear at A is going to be 16.5?
I got 15.
15.5. Is that confirmed? Anybody else get that? 15.5. And that's positive. So it looks like we have positive shear at A and negative shear at B. By the way, we're talking about it. What would be the moment at A? 0. What would be the moment at B?
0.
So we've got our boundaries. So with that set, I'll go ahead and draw a template. Left edge right edge. And for the shear diagram, I'll establish a positive x-axis and a positive shear, and all my numbers will have kilonewtons for force. Now I got a couple things to notice here. You'll see that as I go from the left side to the right side and pass under that 8 kilonewton force, I'm going to have a jump in my shear diagram, so that's a point I'm interested in. Also, I've got no load transitioning into a load, so that's another point that I'm interested in. I have the same scenario here going from one load function to a different one. That's a transition here. So I've got a bunch of other lines I should fill in. So I should add to my template 1 meter, 2 meters, and then this 1 meter, 2 meter section on the right. So starting with my shear at A, what is the shear at A? Positive 15.5. And what's the shear at B? Negative 12.5. So let's see if I can make it all work out. So I know that the change in shear between any 2 points on my graph is the area under the load diagram. So what's the area under my load diagram over the first meter? 0. So there is no change. So I keep my shear at 15.5. It also tells me that the slope of my shear diagram is equal to the load. What's the load? 0, so I have 0 slope. Mr. Rippey! Excellent. The Saints need to cross a few more of those to get to the end zone on the way. A few more horizontal lines, a couple hundred of them maybe.
The first problem in getting better is to recognize you have a problem.
That's right, that's right. The first step to a solution is recognizing that you don't know what you're doing. So I think we all qualify for that, right? We're all moving forward. We're all progressing. Because you know what PhD stands for, don't you?
No diggers.
Almost. High and deep, or finally done. I like cloud, high, and deep. Huh?
A lot of folks told me it's permanent damage.
Oh, I like that one. That's a new one. I haven't heard that one, Mr. Lim. Thank you. I have to add that to my repertoire. So, as we go, this has nothing to do with the problem, by the way. A little segue. You guys look like you were getting a little bored, so I had to. So as we go from the left side to the right side, what happens? I have a change in shear of negative 8. So what's 15.5 minus 8?
7.5.
What's the change in shear from here to here? What's the area of the curve? Which is 0. So there's no change.
This should be positive, right?
Say that again?
Over here,
Over where?
on the moment we solve for the shear at B.
The shear at B is negative.
It's negative. Okay.
I assumed shear at B was down
Oh, okay. All right.
because I always assume, remember, the positive sign convention.
All right.
So positive shear at B is down.
Okay.
So it doesn't change, and we won't pick on Mr. Rippey anymore. But well, not right now. How about that? So the slope of this curve is given by the load, and the load is 0 sloped horizontal line. So we've got kind of this stair-step looking shear diagram going so far. Now what's the change in shear from 2 meters to 6 meters? Will be the area of this part of the curve. That's a rectangle, so base times height is 16. It's negative, so I'm going to go from 7.5, I'm going to subtract 16. What do you get? Negative 8.5, right? This thing is going to be not to scale, but you'll get the idea. And what's the slope of the curve? Given by the load is constant. and negative. So that gives you something that looks like that. I don't think I have it scaled right, but it's close. So now we have a triangular section, and it goes to 0. Bless you. So we know that that 0 value is going to be an additional point that we're going to be interested in. And we'll come back and figure out what that is in just a second. So what happens is I go from this negative 8.5 and I move over to just to the left of my 4 kip force. Well, the change in shear is the area of the curve, which is 0, so I have no change. And the slope is the load, and the load is 0. 0 slope, horizontal line. As I go from the left side to the right side, the change in shear is negative 4. 8.5 minus 4 is negative 12.5. The change in shear of the last meter is the area of the load curve, which is 0, no change, so I hit my shear, match it. And what's the shape of that curve? Well, the shape is given by the load, and the load is 0, 0 slope, horizontal line. So there's my shear diagram. What's the maximum positive shear?
15.
Where does it occur?
Positive shear?
Yes, where does it occur?
At A.
What's the maximum negative shear?
At B, negative 5.
I'm not going to do it to you guys, but I have toyed with the idea in the future in this class to have you work all the problems and then give you 5 to 6 multiple choice questions that come where the answer comes off the work.
Extra credit.
No, all or nothing, multiple choice, right? There's no partial credit for multiple choice. It would be something like that. What's the maximum shear? Where does it occur? What's the maximum moment? Where does it occur? What is the slope of the shear diagram between 2 and 6 meters?
Why are you saying 6 meters?
Between 2 and 6 meters. What's the slope? What's the slope of the shear diagram? It's given by the load, and the load is minus 4. I'm not going to victimize you with that yet. But that is the sort of thing that you might encounter on the FE. So there is a push to make our classes behave more like what you would encounter on the FE. So we'll just have to see. I'm old and crunchy. I like it the way it is. By God, it was good for me. It'll be good for you. That's a imitation of my son making fun of me.
How old is your son?
14 going on 40. What? A little segue. What's amazing me with him, I'm enjoying this actually, it's kind of interesting. It's like an experiment. It's like a science experiment. This thing is growing right in front of me. It's like I put bacteria in a petri dish and I'm watching it grow, except it's 14 years old and it has legs and hair. It just amazes me the amount of information he's acquired in such a short period of time. And it's all encompassing. You guys had that experience? Did you turn 14 and know everything? Maybe it was 13. Maybe it was when the hormones kicked in. All right, so let's start at A. We have 0 moment. And at B, we have 0 moment. Now we got a lot of work to do because we've got 1, 2, 3, 4, 5, 6 different things to do. We need to figure out what X is. How do we do that? We're going to apply our equation, right? So what is the change in shear from this point to this point? It starts off at 7.5 and goes to 0, so the change in shear must be negative 7.5. At the same position, what is the area under the load curve? So to help you visualize that, let me get a different color out here. I'll project that up to the loading curve. So that change should be given by this amount of a load curve. And what shape of that curve? That's a rectangle. Bless you. What's the base of that rectangle? X. And what's the height? -4. So solve that. Put those two together. So I get -7.5 equal -4x. So x is, what's 7.5 divided by 4? What'd you get, Mr. Rippey?
1.875 meters.
Oh, that's going to be a nasty number. These should be rigged so that the number comes out to be like 3, 2. But it is what it is. There it is. So if I know that's 1.875, then I can figure out what this side is, right? All right, so let's begin the process. The process involves that the change in moment now is the area under the shear diagram. So let's begin. What is the area under this part of the shear diagram? 1 times 15.5, I can do that. That's 15.5, and that's a positive area, so we go to 15.5, and we know that the slope of the moment diagram is equal to the shear. And what is the shear? Constant and positive. So I should have a constant. So if I ask you what is the slope of the moment diagram over the first meter of the, what would it be? Positive 15.5. How does the moment change from 1 meter to 2 meters?
It goes up 7.5.
How did you figure that out? 7.5 is the area of this part of the curve, right? It's a rectangle. 1 is the base. Height is 7.5. So what is 15.5 plus 7.5? And what is the slope of the moment diagram? Equal to the shear, and the shear value is positive 7.5. So the slope decreases a little bit. So this slope would be 15.5, this slope would be 7.5. Okay? What's the change in shear over this distance, which we just computed to be 1.875, would be the area of this part of the curve. It's a triangle, so 1/2 base, 1.875 times height, 7.5. .03. I got the same thing. So that should give me a 30.03. We'll leave it like that, but 30 is probably good enough. What's the slope of the curve? Well, it varies because the shear varies. In fact, actually starts off at 7.5 and decreases to 0. So I do know I have a 0 slope there, so that's going to be a maximum. And it will be slightly curved like that. Now one thing you can notice is all of this is negative. It's going to bring it down. And if it's correct, then we've already found our maximum moment. But to make you feel comfortable that you've done it correctly, let's see if all this negative change brings you back to what you expect to be 0. So the next piece we have to deal with is this triangular piece. So this distance is 4 minus that. That should be 2.125. I'll go ahead and pencil that in. So this distance is 2.125 meters. So that times the height, which is negative 8.5. And then divide by 2 plus the rectangle. I get negative 9.03. So I'm going to subtract that from my 30.03. And I get 21?
Yes.
Right there. 21. And that's going to start at 0 slope and get to a larger positive or negative slope. So that's going to curve down. the change from 21 over the next meter is the area of this part of the curve, which is 1 times negative 8.5. So 21 minus 8.5 is 12.5. And the slope is constant. So whatever I finished my slope here is, it's going to be the same. And that's going to have a value of negative 8.5. And then to go from 12.5 to 0 would be the area of this part of the curve, which is 1 times negative 12.5, so it works. And what's the slope of the moment diagram? It's the shear, and the shear is constant and negative 12.5. So it's got a couple of kinks in it. But again, we can now state that the maximum moment in this beam is equal to 30.03 kilonewton meters, and it's going to occur at 2 meters plus that, so that'll be 3.875 meters from A. So a relatively simple looking problem, but a lot of little bitty things to do along the way. So again, I could ask you, hey, what's the bending moment at 2 meters in the beam? 23. What's the bending moment at 7 meters in the beam? 12.5. So if you really needed to know the variation of the moment to be able to do some things, you've already got a lot of points along the way. Is it an equation? No. How many equations would you have to write to solve this problem?
I don't know.
I like Mr. Griffin a bunch, right?
6 times.
Well, there's 1, 2, 3, 4, 5 regions. So you have 5 sets of equations.
So 15.
Oh, just 5 sets.
5. So 10 total. That's a lot of work. I don't think you want to do that. That would be 1, 2. That's 5 free body diagrams to draw. That'd be a mess.
Now, just
So I like this. This is looking better all the day, isn't it? I like those Germans. Those Germans are good. Those 1850s, 60s Germans, they're all over it. All right, any other questions?